is when we have a very large tree. So a large tree might be too complex. So what's going to happen is that if you have a complex tree, when you try to apply to a new data set, then it might not perform well. And here is when we call that the model is already overfitting. Okay? And it leads to poor test performance, poor test accuracy. So we would prefer to have a smaller tree with fewer splits. That might lead to a lower variance and better interpretation. However, we might cause a little bit of bias. Yeah? How do I want to say this? Yeah? So if you have two models, one is very complicated, okay? And then you are able to predict something. Like you want to predict something, you want to predict the weather. You have very complicated model with so many variables that needs to be computed. And it predicts that tomorrow is going to be raining. Okay? And another model. Let's say your auntie at home. Your auntie say that whenever I have this pain, tomorrow is going to be raining. Okay? And she's always accurate. So you would choose a simpler model. So this is just a kind of funny example. Yeah? But basically what we say here is that if you have a simple model and very complicated model, if the prediction is not so much different, then we will want to choose the simpler ones. So how do we choose a simpler one? It could be when your data set is big, yeah? Data set is millions, and you have so many predictors, probably the tree is going to be like very large, yeah? And from the large tree, you don't know what to do. You say, I'm stuck, I don't know what to do. My tree is very complicated. So what you can do is maybe you can just cut down. Cut down here, cut down here, cut down. Just cut. And then you see that after cutting all this, the accuracy is still around the same, the same place. Okay? If you use a complex model, the accuracy level is 70%. If you cut, and then the accuracy level is 65%, it's not so much different. Okay? So you would want to choose the simpler one. Okay, so how do we do the tree pruning? First, we just allow the tree to grow as much as it can, as much as it wants. Just grow. And after they grow, okay, we will, alright, after it grows, then we'll just cut and then we see. Cut and test. Okay? However, this can be short-sighted because a seemingly worthless split early on in the tree might be followed by a very good split. Okay? So let me just read this again, try to understand this. One solution is to build the tree so long as the decrease in RSS exceeds the threshold, but it can be short-sighted. Seemingly worthless split early on might be followed by a very good split. So the best strategy is to grow a very large tree and put it back. Okay. What it means here is that if we are afraid to let the tree grow, okay, and then let's say it grows until here and then we already cut it. And this is what we call as short-sighted because maybe the one that you cut further down the road is going to give you the best split. We never know. So let it grow. Okay, let it grow and then we can prune it back to obtain the subtree. So how do we determine the best way to prune the tree? So first is we select subtree. We select several subtree and we will select the one that lead to the lowest test error rate. Okay, so maybe we can compare, maybe we can have this subtree, this one. Out of all the computing models, we choose the one with the lowest test error rate. And this test error rate can be estimated using the cross-validation. Okay. So we select a small set of subtrees where we cross-validated all the possible subtrees. By cross-validating all the possible subtrees, it will be cumbersome. And then we use the cost complexity pruning, or what we call, in other words, we call it as the weakest link from pruning. It means that we try to consider a sequence of trees indexed by a non-negative tuning parameter outcome. Okay? So So alpha can be from certain value to certain value, and depending on the value of alpha that you choose, this is the alpha is called the cost complexity pruning. So now let's look at this one. Okay. As you can see, this is a modified RSS where we have an actual value versus the predicted value squared plus some alpha. This is the cost complexity multiplied with the absolute t. T is the size of the decision tree. Okay? The size of the decision tree is explained or described by the number of terminal nodes. And here, okay, the tuning parameter alpha, it controls the trade-off between the subtree's complexity and its fit to the training data. So the higher the alpha, the more complex of a tree it will be. Now, how do we build this regression tree algorithm? Again, we use the recursive binary splitting using a greedy approach, where during the first split, we choose the one that will be best explanatory variable that can divide the data into two or more parts. So we use the recursive binary splitting to draw a very large tree on the training data, and then we stop when the terminal node has fewer than some minimum number of observations. Okay. So let's say that's why when you have a very large data set, then your tree is going to be very, very large, because we will only stop when the terminal node has 5 or less observations. If not, then you just, if let's say there are 20 people in here, then you just further split until there are 5 or less. And then to do the pruning, we apply the cost complexity pruning to the large tree in order to obtain a sequence of best subtree. Okay, and this is as a function of alpha. So let's say we use a cross validation technique, the k-fold cross validation, to choose the alpha, which is we divide the training observations into k different folds. Okay. So first is we repeat the step 1 and step 2. Okay. Using all but the k-fold data. So using, let's say k is equal to 10, so we run on the first line, and then we repeat again 10 times. Each time we will evaluate the mean squared prediction error on the data. Okay. And then what we do next is we average the result for each of the value of alpha, and then we pick alpha, which minimizes the average error. So later on you will see that we'll do this using R, and we'll choose the one that minimizes the test error. And then we return the subtree from step 2 that correspond to the chosen value of alpha. So this is one example, as you can see here. So this is the mean squared error, and this is the tree size. So as you can see, when the tree size gets larger, I think the black one or the blue, the dark blue one is the training data set. Okay. Of course, the mean squared error will minimize when the tree gets very large. When this is the complexity of the tree. Okay. As the tree becomes more complex, then the MSE for the training data sets will reduce, because the model actually overfits the training data set. And then this is the cross validation, and this is the testing data set. And you can see as the model goes higher, okay, it doesn't reduce so much. In fact, you see the highest reduction when the size of the tree from 1 goes to 2, and I think it's minimized at 3. Okay, and after that it starts to deviate away. Okay, so here it says that the minimum cross validation error, it occurs at the tree size of 3. In other words, we can say that if the tree size chosen is 10, then for the training data set, the error would be 0.3 something, but on the testing data sets, it's going to be higher. It's 0.4 something, much higher than the training data set. So there's a huge difference over here. Okay, now we are done with the regression tree. Well, the response variable is numerical. Now we want to talk about the classification tree. Classification tree is when the response variable is categorical. It can be 2, it can be 3. Theoretically, it can be more than that, but then you're not going to have a very good model for more than 3 states. So the classification tree is very similar to regression tree, except that it predicts a qualitative response. It predicts that each observation belongs to the most commonly occurring class, which is the mode, the mode of the respondents. So, in interpreting the result of a classification tree, we are often interested not only in the class prediction, corresponding to a particular terminal region, but also in the class proportions among the training observation that fall into that region. So let me just go back to this one, because I just want to show the example. So let's say this assume that this is classification. So this is classified as one thing, another thing, another thing. So let's say this is those who like sweet food. This is sour food, and this is spicy. Okay. Even though not everyone would like what is the first one? Sweet, right? Not everyone in here would like the sweet food. There might be some error, okay? But majority of the people here, they like sweet food. Okay, they like sweet things. And similar to this one, not everyone, but most of you will like spicy, and this one will like the sour food. Right? So we just depends on the mode. But it is not just the mode, but we also like to know the proportion. For example, here, 99% like sweet food. Only 1% doesn't like. Okay? So that is one information that we like to have. Region 2, okay? 85% likes the sour food, but 15% doesn't like it. So this is also another information that we like to see. Because 99% and 85% is, this is different. Okay, so if for the regression tree we look at the RS as something that can minimize the residual sum of squares between the actual and the predicted. Now this is the classification error rate. Okay. So the classification error rate is simply the fraction of the training observation in that region that do not belong to the most common class. Like just now we have like 1% do not belong to sweet food. 15% doesn't belong to sour food. Okay? So this is what we try to minimize. So here the P of the MK hat represents the proportions of training observation in the M region, okay? In the first region, second region, that are from the K class, which is it from the sweet class or is it from the sour class, and etc. Okay. However, the classification error is not sufficiently sensitive for tree growing. So that's why we want to prefer the Gini index. Okay. So the Gini index, what is the Gini index? So we call it Gini impurity index. If possible, we want to choose a variable that we have an impurity. Pure means, for example, like strawberry juice. Pure juice. 100% is made of strawberry. Okay? So if possible, we want to have something like that. That is 100% belongs to this group. Yeah. So in extreme case, that is one example of the extreme case. So this is the formula for the Gini index. Yeah. So the Gini index is a measure of the total variance across the K classes. And then you can take a small value if all of the P hat close to 0 or 1. Which means that this Gini index takes on a small value if your 0% or 100%. Okay, somewhere in the middle will increase the Gini index. So we will choose something that minimizes the Gini index. Whether you are 0% or 100% close to this number will reduce the Gini index. So this is also referred to the measure of node purity. Okay, the purity of the nodes. If this is like 100% young people, okay, then we see no old people here. Or we can say there's 0% of old people here, okay, which means that they are all young people, isn't it? How many of you are more than 40 years old? How many you don't want to tell? It's okay. Then all of us are young, isn't it? Including me. Okay. Alright, so this is an alternative to the Gini index. Now when we look at the equation, nothing gets funny anymore. So this is entropy, which is an alternative to the Gini index. Okay. So since the p hat of the Gini index is always between 0 and 1, okay, therefore I'm so sorry, this one looks like this, yeah. Then what is this? I think this one, yeah. The p hat of log p hat, okay, will always be larger than or equal to 0. I mean, this is, I actually write or I type this lecture myself, and because I develop so many courses, sometimes I just don't have time to really, look at the or improve on the equations. So if you're really confused about this, you can just go back to the book. You have access to the book, right? Yeah, the soft copy of the book I already shared. So the entropy will take on the value near 0 if the p hat are all near 0 or near 1. Okay? So if the Gini index is low, okay, in which the p hat is near 0 or near 1, and then the entropy will take on a value near 0. And it will take on a small value is M node is pure. Okay? So which means that if there is a purity, you are either 0 or 1, where the Gini index is minimized and the entropy is closer to 0. Okay? So the Gini index entropy will not be so much different. It will be quite similar numerically. Gini index and entropy are more sensitive to node purity than classification error rate. Yeah? Because this one we focus on the purity of a certain state. Therefore, they are typically used to evaluate the quality of a particular state. Right? So any of these three approaches might be used when pruning a tree. So you can choose whether you want to choose Gini or entropy, or you want to choose a classification rate. The classification error rate is preferable if prediction accuracy of the final prune tree is the goal. Okay? Because at the end, we want to see how many are correctly predicted, how many are wrongly predicted. Okay? In that case, of course, we want to minimize the classification rate. But if you're looking more towards the purity or impurity, then you would prefer the Gini index or the entropy. Okay, now let's look at this one. So this is one example of the classification tree. Yeah. So first is you have the first split, second split, and etc. I think if you look at the textbook, yeah, I'm not sure whether I have it here. Okay. This is something to do with the medical analysis. And as you can see here, the terminal node only has classification. It doesn't have numbers. There is either no, yes, etc. And what is the size of the tree? The size is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. If I don't miss anything, I think it's 18. Okay? So the size of the tree here is 18. Now, another one thing I want to tell you, okay? It could be that, I don't know what is this, tau. I don't know what is tau. But if tau is A, you go this one. If tau is B, you go here. Okay? And Here is tau again. Okay, if tau is B, you go here. If tau is A, you go here. So it is possible that during the greedy approach, first you choose tau. It is possible for you in the next step you choose tau again. Okay, it doesn't mean that once tau is over there, it doesn't appear anywhere else in the tree. It is possible for you to repeat this case. Okay, so this is the cross-validation result. Just now we have how many? The size of 18, right? It's somewhere here. And you can see this one, it minimizes the trading error rate. But then as you can see, there's a huge difference between the training set with the testing and the cross-validation. So the cross-validation, which is the red, suggests how many? 1, 2, 3, 4, 5, 6. Okay? Some of us might say 4, some of us might say 6 over here. So let's say we choose 6, which minimizes the cross-validation error rate, and this is the prone truth. As you can see from this, where we have val, CA, and so on. Now this is a new tree, the tree that has been pruned, the tree that minimizes the cross-validation error rate. Okay, so now let's ask this question. Now you have learned about the linear model, you have also learned about the tree model. Okay, so the linear model is given on the left hand side and the tree model is given on the right hand side. So which model is better? In machine learning analysis, in data analytics, because we can do this very easily using computer. So to answer this question is, it really depends on the data, and the best that you can do is maybe you can just run many models, and then you can do the performance analysis afterwards. So let's say you are considering between the linear regression and also the tree, the regression tree. So what you can do is maybe you can just run them both, and then you run which one is actually better. Okay? And even when you run the decision tree, you can have many kind of decision tree. You can have a full decision tree, you can have a prone decision tree, or you can have random forest, and etc. And then you compare with the linear regression. If let's say linear regression would be have the highest accuracy, then definitely you choose that one. Plus linear regression is a bit sophisticated. Because not only that it is easy to interpret, but also it is quite simple to understand. Yeah. However, according to this book, it says that if the relationship between the features and the response is well approximated by a linear model, then an approach such as linear regression will likely work well. Okay? And it will outperform the method such as the regression tree that does not exploit this linear structure. So if we believe that relationship is linear, the linear model will be the best model. Okay? However, in real life, we know that it's very hard to find a data generating mechanism in which the relationship is actually linear. Okay? So in this case, maybe you think that, okay, instead of just limiting to linear regression, so you would want to run the regression tree. Okay? Now these are the advantage and disadvantage of tree. Number one is easy to explain, and it more closely to the human decision making, because you look at the first thing and then you look at the next thing, and etc. and etc. And you can display this graphically, which is easy to interpret, easy to understand, and it can handle qualitative predictor without the need to create a dummy variable. So you have your data as it were, and you just feed it into decision tree. Okay. However, the drawbacks of the decision tree is that it do not have the same level of predictive accuracy. Okay. So especially when the relationship is linear, the decision tree might not work well. And the tree can be non-robust. So for example, you develop one decision tree, your friend develop one decision tree, you're going to have a very different decision tree because the sample that you choose is different. Okay? Just a little bit difference in terms of the sample, the whole decision tree is going to be different. So how do you want to rely your prediction or your explanation based on that? Okay? However, this thing can be overcome if we aggregate many decision trees using methods such as bagging, random forest, and boosting. Okay. So I think we all need another break before we go for the bagging, boosting, and decision tree. We'll meet again at 7:30. Okay, and then we talk about the bagging and boosting and etc.